So, any questions before we start? Okay, so I think we'll have a little bit of fun today. Let me start with this definition. We're going to talk about algebraic closures when we get this preliminary stuff. We say F is a normal extension. Okay. Of course, your K and F are fields. F is an extension of field K. If every non-constant irreducible polynomial Kx that has a root in F splits over F. So what it means for an extension to be normal is, so it's an extension F containing K. And it's got this interesting property that if you have an irreducible polynomial Kx and it's got one root in F, then it's got all its roots. Right? That's essentially what it means. And in fact, it's going to turn out to be Galois equivalent to normal plus separable. As a matter of fact. So if you're playing in the playground of, for example, fields of characteristic 0, then Galois and normal are synonyms in that particular context. So let me give you that definition in hand. I may go through a little bit of this, but then I want to talk about algebraic closed fields and show how to build them. Let F be a field, following conditions are apply. Number one, every non-constant polynomial f of x and f of x has a root in f. Number two, it splits. That is, every non-constant f of x and fx splits over f. 3, f of x and f of x is irreducible if and only if the degree of f of x is 1. Or, well, there is no non-trivial algebraic extension of f you might say, well, what do I mean by non-trivial here? Well, f is always an algebraic extension of itself. And so another way to put that is there's no proper algebraic extension of f. And there's a field K and F. Such that F is algebraic over K and every polynomial in Kx splits in Fx. Fx, Kx splits in Fx. Right. By the way, here's the other edge of the sword of trivial. If, for example, for equivalences, you might see why this is true for K being algebraic inside this. But if you already know that Fx is algebraically closed, then this certainly holds. If you believe these other four, this certainly holds with K being, just set K equal to F, right? Because then F is algebraic over itself and every polynomial in Fx splits, right? So let me kind of talk us through it. Every non-constant has a root, right? That sort of means it splits, doesn't it? Right? Because take a polynomial in Fx, it's got a root. Factor that root out. Now you've reduced the degree by 1. But that other polynomial has a root as well, and you just continue this process inductively until you factored it all the way down into linears, right? Of course, this statement makes this clear because certainly if your degree is 1, then you're irreducible. That's true for any polynomial field. Degree 1s are always irreducible. On the other hand, for the other direction, if you have anything of degree 2 or higher, it splits and is therefore not irreducible. Right? And I think we talked about this one last time. There's no non-trivial algebraic extension. If there was a non-trivial algebraic extension, then there would have to be something algebraic over F of degree bigger than 1. And so that would necessitate the existence of an irreducible polynomial of that degree, right? And by what we know already, that can't happen. Right? So, yes.
Is the irreducible one, so is that only for like it's equivalent to statement to like the splitting thing? Or is that in general it's your
Okay, so if we're talking about 3, this direction is always true for any polynomial over a field, doesn't matter. This direction is what depends on the other axis.
Dr. Cordova, do we say that f of x and k of x splits over f of x or splits over f?
I said splits in F of X. Sometimes we say split over F. They're synonymous.
Splits in f of x is synonymous with splits.
Right, I like it. Yeah, so you say it splits over F,
Okay.
which means that all the roots are in F, or splits in, I think that is an element in Fx. Okay. So, any field satisfying 1, hence all of these. Statements is called algebraic closed. Let me give you a formal definition here. So. Definition. Field extension of F. Field extension, let's say. F and F bar. Is called an algebraic closure. Of F, if. Okay, so you might have heard these kind of words thrown around the campfire a little bit. What do you suppose that we're going to demand? Don't you hate this? I'm asking what the definition should be, but what do you think we should demand of an algebraic closure? What should it?
Every non-constant at polynomial like f, like without the bar x, has roots in f over bar x.
Okay.
Well,
And then, yeah, and there, I agree. And there's probably one more thing that we want to demand. That
F bar is algebraic.
was it?
Isn't F bar algebraic?
That's it. I want F bar is algebraic over F, and two, F bar is algebraic closed. Which is a more compact way to say what you just said. So the complex numbers is algebraically closed, right? This is again old folklore, but it's not an algebraic closure of say Q because it doesn't settle about this problem. Complex numbers is too big to be algebraic over Q. However, the complex numbers is an algebraic closure of the real numbers, right? Because certainly the complex numbers once again algebraic closed, but the dimension of the complex over the reals is 2, which makes that an algebraic extension.
Does 5 in that theorem guarantee that every algebraically closed field is the algebraic closure of some other field?
Yes, so
Oh, at least it's.
any algebraically closed field. Yeah, so if you have an algebraically closed field, it is the algebraic closure of itself, right? The question about whether you can find the proper subfield of finite index, that's a more delicate question. Okay, so here is, we're going to do a big construction now, and it's going to be so fun, and you're going to help me too. We're going to be talking about it forever. So let me give you this big theorem. Notice how I didn't say the algebraic closure, but I said an algebraic closure. We've got the best algebraic closures. But it's going to turn out that algebraic closure is, you can loosely say every field K has an algebraic closure, and any two of them are chaos morphic. So So any field has an algebraic closure, that's first strike. And if F1 and F2 are algebraic closures of K, then are K isomorphic. So not only are they isomorphic as fields, but they're even K isomorphic. They're isomorphic via an isomorphism that freezes K. Okay. How do we do this? How do we build an algebraic closure? So suppose I start with field K, and what do I do? Right, there are some actual, there's different proofs out there. I'm gonna do one that I think is decidedly easier, and if you look in Hungerford's proof, it's a lot of set theoretic jargon. They kind of, and miss the wheel on nothing. But I'm a commutative algebraist, and I'm gonna do something a little different. Now, intuitively, how do you think? Okay, let's forget about being careful mathematically. If I have some field K, how would I go about philosophically building its algebraic closure? Yeah.
Adjoin all the roots.
Okay. Adjoin all the roots of all the irreducible polynomials that I can find in there, right? And we've talked about adjoining roots of a single irreducible polynomial. And in fact, more generally, we've talked about adjoining roots of polynomials when it wasn't irreducible. Remember it, but the dimension might not be full degree if it's not irreducible. And so now I can take any finite collection of polynomials and adjoin those roots just by taking all the finite and multiplying together, making one big long polynomial and join the roots of that. But that doesn't help me with the infinite case, right? So how would I go about that, right? So the problem is there's infinitely, intuitively, this is the right thing to do. You just take all the roots and throw them in. But what does that mean? And in fact, here's part of the problem. You're starting with a field and it's our ceiling already. Roots from where, right? That's one of the problems because at the outset, I'm talking about K as the daddy Mac, right? I'm not talking about it being inside some bigger mathematical structure. So where am I getting my roots from? Right, so that's a little bit of the problem. So here's something we would do, because I love rings. Let's do the following. Let's build this set. And you will see that the spirit is in your all's idea. I'm going to build this. And in fact, it doesn't matter. I don't even need them to be irreducible, just any non-constant polynomial, right? I don't want zero. Okay. Now I'm going to build a ring as follows. Okay, so this gives some collection of polynomials that are irreducible, right? I introduce a new variable. For indeterminate. X sub f. Now what I want to do is I want to build a following ring. This is a polynomial ring with a whole bunch of variables. In fact, there's one variable for every irreducible polynomial that I can. Right, agree with that? So for every different f in here, there's a new polynomial variable. Agree? This, in a certain sense, this sort of helps me with what I was doing before, because one of the problems was is K doesn't live inside something bigger. Well, now it does, right? It's living inside this ginormous polynomial ring where I have join a new variable for every one of these irreducibles that I found here. And now I am going to create an ideal. Uh, and this is the ideal. I want to do this ideal x bet right. So take this one and plug in that, right?
So you're creating a variable for each f. So if you have like f1 and f2 and s, would it be like f of y f and f of x f? Like, are you changing what you like plug in there every time?
Right. So
Okay.
this ring right here,
Mhm.
the variables are the x sub f's, right?
Mhm.
And so yes, for the irreducible polynomial here, that's right. X is sort of discarded, right,
Okay.
in a certain sense. And I plug in its identifying variable. Right. Okay. I guess, let's see, so we look at the ideal generated by these polynomials. All right. Now, I guess the first thing is I should start with you. Well, let's suppose not. Right, we're talking about computer ring of identity here, so that's almost true. So what would that mean? One equals, let me call it G F one X F one plus G two F two X F two plus G N F sub n, F sub n.
And those are, the G's are in K.
Right, where the GIs. Now, of course, the G's, let me point out, of course, the G's could involve multivariables from here. All of them involve finite remaining. Right? Okay, can anybody see how to get contradiction into this? I'll give you a hint, there's a way to get, I mean, obviously we've got one here, there's a way to get zero on the other side. Oh. Yeah, I'm glad I went through this. Here we go. There we go. I'll do that later. And let's modify that. Okay, so how can we get zero on the side? Well, let me skip over this now because somehow it's escaped me. I'll fix this in a moment. But for right now, we'll take this as I is proper ideal. Actually, maybe going down the road a little bit, help me out here. So. I is proper, we will demonstrate later. If it's proper, then I think we all agree with that. Any ideal between a maximal ideal. So consider I'm gonna call this K1. Is this construction here? Modulo this ideal. Well, actually, M. Now, this is a field. And contains K. Right, because actually, you know, the typical element of this is a polynomial in these variables modulo M. So K embeds in it's in a one-to-one fashion. This is a field because that's a maximal ideal. This field contains K. And um, each f of x kx has a root in K1. And the reason is because of what I modded out by. Notice f mod x of f is essentially a root of this polynomial, right, when I killed this idea. And so what I've done is I have created I've created a field irreducible in kx has, in fact, every irreducible has a root in K1. My root. Well, what's the problem here? Well, there's two problems that kind of jump out at this point. Is remember what we're trying to do is build an algebraic closure, right? And one of our equivalent conditions in algebraic closure is that every polynomial in Kx has root. And so why doesn't this work? Or why might this not work at this point?
K1 might not have all of the roots of K1 adjoining.
Well, in fact, that's part of the problem. So remember, saying the polynomial, every irreducible polynomial has a root in K. But see, now the problem is that you've got your f of x that has a root now up in K1. All right. But when you factor that out in K1, that polynomial, there's no guarantee it's got a further root in K1, right? That's the problem. And in fact, not only that, I've thrown in a whole bunch of new garbage, right? So there's no guarantee at all that this is algebraically closed because I haven't really solved the problem because what's true now is every irreducible polynomial Kx has a root up to here in K1. But now you've got new polynomials in K1 that don't have a root, so you might not be able to break that down further. So why did I go through all this? What now? Yeah.
Do you iterate inductively?
That's what you can do. So now, that is the first step. Now, repeat to build K2 such that every f of x in K1x has a root in K2, etc. And in general, every f of x and k in x just keep going. So you have k, our base field, contained in K1, contained in K2, contained in K3. And let F let it be. Yes.
Is each case K2 and stuff, are they all modded out by M? Or like,
That's right.
oh,
Every time you do that same stupid thing over and over.
okay,
Right.
so it'd be K1 or like that whole thing, mod M. Is it all that mod M?
Yeah, but I wouldn't think about it that way, because it's gonna be a mess, but yeah, because what you do is you now take the irreducible polynomials here, adjoin them, a variable for each one of these, and you get a different I and a different maximal ideal, and you just keep this process going. But this, actually, this kind of shows you the power of induction.
Well, Dr. Gordon,
Mhm.
we don't know that this process terminates, correct?
Certainly does in union.
Okay.
You can take the union of those fields. I'll prove this works. In fact, if you're doing something like constructing the algebraic or an algebraic closure cube, it won't ever terminate a finite number of steps. If you're doing the algebraic closure of the reals, it'll terminate the first step. So, well, it depends on what you mean by terminate, I guess. But the complex numbers will terminate in the first step because the only irreducible polynomials are linear. So essentially, you're adjoining nothing. Right? Nothing diminishes. Okay, the first thing I do is I claim that this union of fields, right? Well, let's see. So let x, y be in F, then x is in K n, y is in K m. Therefore, x and y are in K sub max in M. Right? So x minus y is in K max in M, which is contained in F. Okay, so it's a subgroup. Same. Also, xy is in K max in M, which is in F. By the same sort of logic. So it's a ring now. And it's a field, in fact. Also, x inverse is in K n. So we're caveat if x is not 0. Everybody okay so far? So this is honest to goodness field. And now all we have to do is show that this field, that every well, we need to show it's algebraically closed. Well, no, actually, I'm gonna show it's algebraically closed and then. Okay, so first thing I'm gonna do is I'm gonna show that F is algebraic. Alpha be algebraic over F. So alpha is a root of, let's say, I'll make it mnemonic there. Beta n minus one x n minus one beta one x plus beta zero and f x. Okay, so alpha is the root of that. And of course, this means that the beta i's are in F. Well, what does that mean? Well, F is a union of a bunch of this crap, right? So that means all those betas are in, like beta one is in K1, beta two is in K2, so forth, so on, right? So there exists in the natural numbers such that beta k is in so there's sort of a largest index that contain, well, there's a smallest index, one large enough to contain all the coefficients, right? Therefore, x to the n plus beta n minus one x n minus one is beta one x plus beta zero is actually in k n x. And I was going to say at this point, maybe I being overly careful here. I was going to say that alpha is actually in kn plus one, right? Because that's the root of this. However, if I want to be super careful, maybe the root that comes up in the next step is actually not alpha, right? But for sure, it'll come up in how many steps? Well, in less than n. So certainly alpha is in k capital N plus n. I think we can agree with that. Because in kn plus one, this will be of degree, the irreducible part will be of no more than n plus one, n plus two, you drop through by two, and finally you get down to where alpha's got to be in here. But doesn't matter, this is in F. So F is algebraic closed. Yes.
How do we know that each K or beta K is in K?
Well,
Like,
because
those coefficients.
let's say beta zero is in K zero, this is in K, well, this is in K something, K something, K something. Look at all your somethings and take the biggest one because it's contained, and so that biggest one will contain all of them.
Dr. Bergman. If we have something that's like transcend, like, wouldn't we also show this by saying that F has no transcendental elements?
Oh, it might.
It might
I don't see why not.
over itself.
See, that's the thing. So what we've got now is F is algebraically closed, we also need that f is algebraic over k. So how do we solve that problem? Any ideas?
You mod up and change the number.
No, not that. So I'll let k bar equal the so that is, this is the set, let k bar just be the set of gamma and f, such that gamma is algebraic over k. So in other words, what we're doing is, in this step, we're tossing out any possible transcendental elements. And this works for the following reason. The set of all algebraic elements over K actually forms a subfield. This is something that we've already proved, the set of algebraic elements, right? Now, this K bar, by definition, is algebraic over K, and it's algebraic closed. So, okay, any questions on that?
Dr. Bergman?
Mhm.
How do we have the K bar is algebraically closed?
Okay, so. I mean, I guess. Could have done it. Right. Because. So I'm going to take K bar to be this definition here. This is algebraic over K. Now suppose it's the same sort of thing. Alpha is a root. Right? But now, each beta I is in K bar. So each beta I is algebraic over K. Right? And now you essentially just go through the same proof here. Right? Because each of these is algebraic over K, that must mean that they actually come out of these KNs, but they're guaranteed to be algebraic, right? And so, once again, that means that this alpha is in one of these KNs, only the part that's restricted to being algebraic over K. So the proof is essentially same. Does that clear it up?
Yeah. Okay,
other questions? All right, we'll fill in that last detail next time. You all did get my email, didn't you, about I've got a defense to go to for a couple hours, but I'll be back this afternoon. So, any questions? All right, we will